Okay, let's continue with our Lewis Structure VSEPR Geometry's Muddy Points questions that you had. And so I think we had a lot of questions about resonance structures, and that's fair enough. So the last one we ended part 1 with was the carbonate ion. Let's try the phosphate ion for more practice. PO4 3-. The phosphate ion has the following Lewis structure. 4, 6 is 24, and 5 is 29, plus 3 is 32 electrons. So phosphorus is in the middle, and we arrange our oxygens around 1, 2, 3, 4, and I apply 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, that's it, and I have a charge of 3-. 2, 4, 6, 8. That looks fine, doesn't it? 8 electrons, octet satisfied on the phosphorus, and so on. So that looks fine. That's an acceptable Lewis structure. Now, the hint that I gave on the slide today, it said investigate the possibilities of any resonance structures for the phosphate ion, and if so, draw them. Well, how would you be alerted to the idea of using resonance here if there's really no need to make a double bond? Phosphorus already has 8. Well, I will ask you on the exam to label these atoms with formal charges, and I'll ask you to do it because I don't think we're really in the habit or practice of doing it regularly. But let's see what happens. Phosphorus is under nitrogen, and so it has 5 valence. So valence minus half of the bonding and all of the non-bonding electrons, 5 minus 4 in this case, is plus 1. So that's not 0, and we usually want our central atom to be really close to 0 or 0. So you can't get much closer than plus 1, but I wonder if there's an opportunity to make that 0. Each single bond oxygen with 3 pairs of electrons here has a formal charge of 6 minus 1, 2, 3, 4, 5, 6, 7, and so that's minus 1 all the way around. And that's why I've got, or that's in keeping with, a negative 3 charge on the ion in total. So, is there a way that I can make these formal charges, or at least some of them, closer to 0 or 0? And how would I do that? What is the effect, let's just see, of taking that pair, because I don't want to disrupt the 8 electrons that I have around oxygen either. But what is the effect of taking that pair and putting it here? And you're thinking, well, you already have 8 around phosphorus. Why would you do that? Because phosphorus is one of those elements, that has, well, phosphorus is the cutoff point. That's the threshold. Z equals 15. So anything above phosphorus, or phosphorus itself, is capable of doing what's called back bonding, and therefore accepting more than 8 electrons if there's good reason to. So if I took this pair and put it here, that would make 10 electrons around phosphorus. And the effect of that on the formal charge would be to make the oxygen a 0. And this phosphorus would then be, if I did that, how would it change? The formal charge would then be 5 minus 1, 2, 3, 4, 5. It would actually make it 0. So, another, because in this case this one is possible, feasible, but another possible Lewis structure would be with a phosphorus and 1 double bond. But because there are 1, 2, 3, 4 possible places for that, there would be 4 resonance structures. Okay, I'm not going to draw them all out here. I'm going to say this plus 3 more resonance structures, so you know what those would be. Now I'm going to push the limit here because, and let's update. This would now have a formal charge of 0, and the single bonded oxygens would still have a -1. But this would be 6 minus 1, 2, 3, 4, 5, 6. Remember, the double bond to an oxygen on the outside of the molecule is very favorable. So because phosphorus can actually hold not only 2, 4, 6, 8, 10 electrons, but 12, yeah, why not? Let's try it. Have room? Sure. Let's put it here. Let's take this pair of electrons and bring it down and make a double bond there, so that I have phosphorus, double bond, and single, and single, and I would have a couple of different resonance structures there as well that would have 2 single and 2 double bonds. And so now phosphorus has 2, 4, 6, 8, 10, 12. Its formal charge is 5 minus 1, 2, 3, 4, 5, 6, or a -1. Okay, phosphorus is not that electronegative. I'm kind of liking this one, but this is now a 0, and this is a 0, and this is a -1, and this is a -1. So it's still adding up to a -3. So I have plus more resonance structures. So I'm just wondering, which one would you promote as being a better Lewis structure arrangement, 1 double bond or the series with 2 double bonds? And you always want to base those answers on formal charges, because first of all, one has 10 and the other has 12 electrons on the central atom, but phosphorus is okay with either one of those situations. But I end up with a formal charge of 0 on the central atom here, whereas I don't here. And I have 2 atoms with 0s and 3 -1s, but so do I have it here, 2 with 0 and 3 with -1s. However, in this one, it's the more electronegative element, oxygen, that has the negatives associated with it, whereas here I have a central, and I'd rather have a central. And phosphorus is not as electronegative, not nearly as electronegative as oxygen. In fact, it's interesting that hydrogen and phosphorus have the same electronegativity, interestingly enough. So I tend to go with this one and 3 more resonance structures as being the best. And again, the argument for choosing comes down to formal charges. But something that we might have overlooked was that phosphorus could take 10, and we may have left it there. So watch for little clues in the way that a question is worded, or obvious clues in the way the question is worded. Draw all the possible resonance structures. Yeah, so just be on the alert for some good pointers there. We did carbonate, we did phosphate. One that you should probably try, I'll leave that for you. I don't think I did it. I could be forgetting, but and that's the sulfate is another good one. And we did ammonium, we did acetate. Let's do, let's get away from the ions and let's do PCl3. Oh, can I bring this back here for a moment? Because we didn't do the geometries on the phosphate. We got carried away. I got carried away on the resonance. So, the same question comes up. Which one of these Lewis structure possibilities should I be using to determine the VSEPR on? But if you notice, this one has 4 electron groups, So does this one, and so does this one, because when I'm counting electron groups, I count the multiple bonds as one each here. So at 1, 2, 3, 4. So on each of them, the central atom has 4 electron groups. And so on each of these, the electron group geometry is tetrahedral, and the molecular geometry is also tetrahedral, and the hybridization state of phosphorus is sp3. All right. Okay, let's do PCl3. So again, adding up electrons, 3 7s, 21, and 5 is 26 electrons. And I'll put my phosphorus and arrange the chlorines around. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I'll put the last pair here for 26. Okay. That is my Lewis structure. And now I want to determine the geometry. I have how many groups around the central phosphorus atom? 1, 2, 3, 4. So it is my electron group geometry is tetrahedral. And I have one lone pair, so I'm not going to draw that as a stick or a bond, but do this, and then I will do this. Chlorine, chlorine, chlorine. And I bet you're wondering right now, hold on. On the last one with the phosphorus and oxygen, you looked at the formal charge and said, we could do better than that. Let's make some multiple bonds. The one thing about the halogen atoms is that they're quite happy being a single bond to a halogen with a single bond to itself with 3 lone pairs. Let's just look at the formal charges on this for a moment. We can use this one. Chlorine, 7 valence, so 7 minus 1, 2, 3, 4, 5, 6, 7. So that actually has a formal charge. I'll mark it on here. It's the same thing, of a 0. So all these halogens with single bonds and 3 lone pairs, which we're seeing often on the outside, very electronegative. These bonds are polarized towards the more electronegative atom, right? Okay, and the phosphorus has 5 valence, so it's 5 minus 1, 2, 3, 4, 5. Oh, so phosphorus does have a 0 formal charge here. So you see why, even though phosphorus can take more than 8, it can take 10 or 12, I didn't choose to take this pair, and put it down here and make a double bond and resonate it through either here or here or here, because there's no motivation to do it. Phosphorus is already 0, the chlorines are already 0, everything's happy. So I leave it like that. I have one Lewis structure. The electron group geometry around phosphorus is tetrahedral, but the molecular geometry is trigonal pyramid. Don't say planar because it's not flat. And the hybridization state of phosphorus is 1, 2, 3, 4, so the hybridization state is sp3. We throw in a bond angle here, the chlorine phosphorus bond angle on that trigonal pyramid is 109.5. Maybe it's a little less, but I would say it's about 109.5, and you'll be 100%. Now that's PCl3. I thought we would do PCl5 for comparison. So let's turn this around. One thing I noticed after class today is brought to my attention that we've done lots of examples on video with hybridization states, but we don't actually have an example using the hybridization state of sp3d and sp3d2. I hope I'm saying this at the right time. Oh, all right, folks, that is my drive picking me up, who's just texted me, so maybe I better finish with PCl5. Okay, 5 7's 35 and 5 is 40 electrons. Phosphorus. See how fast you're going to be able to do these on the exam. Do them carefully though. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. That's big. There are a lot of electrons on phosphorus pentachloride. So I have 2, 4, 6, 8, 10 on phosphorus, but it's okay because phosphorus is that threshold element, including it after which we can back bond up to 10 or 15, or not 15, 10 or 12 electrons on the central atom. What is the formal charge on this phosphorus? Valence minus, so 5 minus 1, 2, 3, 4, 5, and no lone pairs. So actually, the formal charge is 0, and we just saw that the halogens singly bonded with 3 lone pairs, so 7 minus 1, 2, 3, 4, 5, 6, 7 is also 0. So do you see? There's no motivation to move those electron pairs to make double bonds and so on and try and get that phosphorus to 0 because it's already there. So there's no resonance structures here. This is the Lewis structure. So we're ready then to do VSEPR on this. So back to the count, 1, 2, 3, 4, 5 electron groups around phosphorus. 5. And so the electron group geometry is, not tetrahedral, there's 5, so what is it? Trigonal bipyramid, right? And the way that I draw my trigonal bipyramid is, I should probably use a pencil, but no, because there's 5, it's okay. I do this triangle that's not the best triangle. I don't want it to be perfect because I'm trying to give the impression that it's a flat triangle sort of coming out and going in, like slicing here a card right in. So I'm going to put my phosphorus in the center, and then this line here is a bond to chlorine and a bond up to chlorine, and then a bond out this way, and this way to chlorine, chlorine, and chlorine. And then we want to add our lone pairs. So I see that I have a chlorine in each of my plane positions, and one up and one down. So these 3 are flat, and then this one's popping up and this one's popping down. And so we note that this chlorine, actually, this bond angle is 90, and this bond angle is 90, and this bond angle is 90. Same thing on the bottom. So this position, this chlorine actually has 3 90-degree neighbors, whereas one on the plane only has 2 90-degree neighbors, and this neighbor is 120. From here to here to here is 120. So I don't have any lone pairs to place on the central atom, but if I did, that's why they go on these flat positions. Anyway, I don't here. So my electron group geometry is trigonal bipyramid. My molecular geometry, or shape, of the molecule is the same. It is a trigonal bipyramid. And the hybridization state of this central atom phosphorus is what? I need 1, 2, 3, 4, 5. So this is S, there's 1, P3, that's up to 4, D. So that is my hybridization state of phosphorus. Great. Okay, I'm really making this person wait, but I want to finish this with you. Can we do SF6? Yeah, let's do SF6. Hold on. So fluorine is 7, 6 7's 42, and sulfur is under oxygen, so that's 6. So I've got 48 electrons. Sulfur 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Okay, they're getting impatient. 48. Wow. So what is the formal charge on sulfur here? Sulfur starts with 6 valence, so it's 6 minus 1, 2, 3, 4, 5, 6. It's actually 0. Everything is 0. So this is the one, the only, the best Lewis structure for SF6. But let's do VSEPR. Oops, sorry. And on it. So with 6, let's see how I already know then what the hybridization state is, because I just need electron groups. 6 groups. I need 6 atomic orbitals to hybridize to make 6 hybrid orbitals. So it's sp3, that only brings me to 4, d2. This is the max, sp3d2. So there's 6 hybrid atomic orbitals, all of the same energy, degenerate as we said. And now I want to draw this structure. So when I have 6, I draw a parallelogram like so, with a position popping out of the center and one down below, and then I'll fill it in. And I'll just use another color. So I have my sulfur in the center, and I have a fluorine here and here, and then I have them at each corner here. So 2, 4, 6, 8, all the fluorines are dotted with their electron pairs, and the electron group geometry is octahedral. The molecular geometry is octahedral. Let me just convince you that this is an octahedral if I did this. Right? See how it would be 8 sides of equals. Okay, octahedral, and all the bonds are 90, and bond angles are 90, and the hybridization state is sp3d2. We did CL3. Yeah, I think that's great. Okay, so thanks for watching, and good luck with your studying on this stuff.